A Toyota engineer got laughed out of a Detroit conference in 2019 for presenting this material. The same material is now mandatory on every Lexus LFA successor and is quietly showing up in BMW, Mercedes, and Ferrari production lines. And a leaked internal memo from a major American automaker states, "If this scales to mass production, our entire aluminum supply chain becomes obsolete within a decade." This is not a concept, not a prototype, not a lab experiment. It is in production vehicles right now. And the reason you haven't heard about it is because the companies it threatens most have a financial interest in you not knowing it exists. Here's what's actually happening. And rule number 5. The application of this material that will directly affect what you pay for your next car comes after you understand why aluminum became dominant in the first place. What aluminum actually does on a car and why it's already losing. Aluminum replaced steel in structural and body panels starting in the 1990s for one reason: weight. Every 10% reduction in vehicle weight produces a 6 to 8% improvement in fuel economy. Audi built the first mass-production all-aluminum body with the A8 in 1994. Everyone followed. Lighter cars, better economy, better performance. The problem is, aluminum has a ceiling. It corrodes at joints. It fatigues under repeated stress cycles. It is expensive to repair after collision. An aluminum body panel repair costs 3x a comparable steel repair. And it conducts heat, meaning thermal management in electric vehicle battery housings becomes a constant engineering battle. Japan found the ceiling and went through it. The material is carbon fiber reinforced thermoplastic, CFRTP, and it changes everything. Traditional carbon fiber, the kind on Ferrari hoods and McLaren tubs, is carbon fiber reinforced polymer using thermoset resin. It is extraordinarily strong and light. It is also extraordinarily expensive to produce, takes hours to cure, cannot be recycled, and cannot be stamped in a mass production press, which is why it stayed in supercars and aerospace. Toray Industries, a Japanese materials company based in Tokyo, spent 20 years solving every one of those problems. CFRTP replaces the thermoset resin with thermoplastic resin. The result is a material that is stronger than aluminum at 40% of the weight, can be stamped and formed in under 60 seconds in a standard production press, can be welded ultrasonically like plastic, and can be fully recycled at end of vehicle life. According to Toray's published material data, CFRTP structural components show tensile strength of 600 megapascals against aluminum's 270 to 310 megapascals, nearly double the strength, less than half the weight. Stampable in a production environment. Toyota and Toray have been jointly developing this since 2012. Rule number 1 is understanding where it already is in production. The Lexus LFA used traditional carbon fiber throughout its tub. The next generation Lexus flagship is being engineered around CFRTP structural components. Honda has already deployed thermoplastic carbon fiber composite in the rear floor structure of the current Acura NSX. Subaru, through its aerospace division, is producing CFRTP components for the BRZ platform and the Japanese bullet train. The Shinkansen N700S series, introduced in 2020, uses CFRTP in its primary body structure for the first time on a high-speed rail vehicle. A vehicle doing 320 kilometers per hour under constant vibration stress. Real-world validation at a scale no car manufacturer test program can match. Japan just replaced aluminum on cars and nobody is talking about it. Rule number 2 is the electric vehicle angle. And this is why every EV manufacturer on Earth is watching Japan right now. Battery weight is the single biggest limitation holding electric vehicles back. Not charging speed, not battery chemistry, weight. And here is why that matters more than anything else in the EV conversation right now. The current Tesla Model Y weighs 2,003 kilograms. The battery pack alone accounts for 480 kilograms of that. Nearly a quarter of the entire vehicle mass sitting on the floor, doing nothing but storing energy and adding rolling resistance. Every single kilogram you remove from the vehicle structure around that battery directly extends range without adding a single new cell, without improving chemistry, without touching the powertrain at all. You are getting free range purely by making the car lighter. A full CFRTP body structure on a Model Y-sized vehicle reduces structural weight by approximately 180 to 220 kilograms compared to the current mixed aluminum and high-strength steel construction Tesla uses today. That is not a small number. At Tesla's published range efficiency figures of approximately 6 kilometers per kilowatt-hour in real-world conditions, that weight reduction translates to 40 to 55 additional kilometers of range on the identical battery pack. No new chemistry, no additional cells, no larger pack, no increased cost, just lighter structure, delivering range that currently requires a battery upgrade to achieve. For context, Tesla charges $8,000 to $11,000 to upgrade from the standard range to long-range Model Y. CFRTP body construction delivers a meaningful fraction of that range improvement for free, embedded in the base vehicle structure. Every EV manufacturer's financial model for battery sizing, range tiering, and upgrade pricing is built on current structural weight assumptions. CFRTP breaks every one of those assumptions simultaneously. But the Tesla example is actually not the most important EV application of this material. The most important application is what Toyota is building right now. Toyota's solid-state battery vehicle, projected for 2027 to 2028 production, is being engineered from the ground up with CFRTP structural components specifically to maximize the range advantage of the new battery chemistry. Solid-state batteries deliver approximately 2x the energy density of current lithium-ion cells at roughly 40% less weight for equivalent capacity. Toyota is pairing that battery with a CFRTP body structure that is 40% lighter than aluminum. They are compounding two weight reduction technologies simultaneously. The material and the battery are being co-developed as an integrated system from the first engineering sketch. That is not a coincidence. That is a deliberate strategy to produce an electric vehicle with a range figure that no competitor using conventional materials and conventional batteries can match without spending significantly more money on cells. According to Toyota's internal engineering roadmap, portions of which were presented at the 2023 Battery EV Technology Conference in Nagoya, the combined weight reduction from solid-state battery chemistry and CFRTP body structure is projected to deliver a vehicle in the 1,400 kilogram range with a 500 kilometer real-world range. The current Tesla Model Y long range weighs 2,003 kilograms and delivers 533 kilometers of EPA-rated range. Toyota is projecting a vehicle 600 kilograms lighter, delivering comparable range with a battery that costs less to produce. That is the competitive position Japan is building toward. And they are building it with materials that American and European manufacturers do not yet have the production infrastructure to replicate at scale. Rule number 3 is the repair and insurance cost revolution that nobody in the automotive financial industry is pricing in yet. And when they do, it will change which cars people buy. Aluminum body repair after a collision costs 3 times the equivalent steel repair. Not slightly more, 3 times. The reason is metallurgical. Aluminum work hardens when struck. The crystal structure of the metal changes at the impact point, making the area harder and more brittle than the surrounding material. You cannot heat it and straighten it the way you straighten steel. You cannot use a slide hammer and pull the dent. The panel either comes off and gets replaced entirely or gets filled. An aluminum filler work on a structural panel is a repair that any competent inspector will identify immediately, destroying resale value. Specialized aluminum repair requires technicians certified specifically for aluminum bodywork, equipment that cannot be used on steel, dedicated work areas to prevent aluminum contamination of steel repair areas, and repair times that run 40 to 60% longer than comparable steel work. This is why insurance premiums on aluminum-intensive vehicles, the Tesla Model S, the Audi A8, the Jaguar XJ, the Land Rover Range Rover, run $400 to $900 per year higher than comparable steel-bodied vehicles in the same value bracket. The premium is not for the car, it is for the repair cost profile of the material. CFRTP changes this repair equation completely, and in ways that the insurance industry has not yet fully modeled into premium pricing. CFRTP panels After a low-speed collision impact below approximately 15 kilometers per hour do not deform permanently the way metal panels do. The thermoplastic matrix absorbs and redistributes impact energy elastically, meaning the panel flexes, absorbs the force, and returns to its original geometry without permanent deformation. The paint may crack. The panel itself is undamaged. In a parking lot impact that would put a crease in an aluminum door panel requiring a $1,200 repair, a CFRTP panel bounces back. The repair cost is zero. Above the elastic threshold in impacts, severe enough to cause structural damage, CFRTP panels crack cleanly and are replaced as complete units. No straightening, no filler work, no specialized metalworking certification required. The damaged panel unbolts. The replacement panel bolts on, paint, and done. The repair process is closer to replacing a plastic bumper cover than repairing a metal body panel, but with the structural properties of metal. According to preliminary repair cost modeling published by Thatcham Research in the United Kingdom, the independent organization that establishes insurance repair standards across the European market, CFRTP panel replacement in a standardized low-speed impact scenario costs 22% less than equivalent aluminum repair when measured across a statistically significant repair sample. 22% less. On a vehicle segment where insurance costs $2,400 per year, that 22% repair cost reduction translates to meaningful annual premium savings. Once insurers adjust their actuarial models to reflect the real-world repair data on a vehicle you own for 10 years, the compounded insurance premium difference between an aluminum-bodied vehicle and a CFRTP-bodied vehicle could realistically reach $3,000 to $6,000, depending on your location, driving record, and coverage level. That is money that currently does not appear in any new vehicle total cost of ownership calculator because the repair data is too new and the production volumes are too low for insurers to have recalibrated. The buyers who understand this now are the ones who will make purchasing decisions that look prescient in 5 years when everyone else catches up. Rule number 4 is the recycling story that makes CFRTP not just commercially compelling, but politically unstoppable. And political momentum in the automotive industry moves faster than engineering momentum. Traditional carbon fiber composite, the thermoset resin variety used in Ferrari hoods, McLaren tubs, and aerospace structures cannot be recycled in any economically viable way. The epoxy, or polyester resin matrix, and the carbon fibers are chemically bonded through an irreversible curing reaction. Once cured, the material is permanent. At end of vehicle life, thermoset carbon fiber components go to landfill or industrial incineration. There is no recovery. There is no reuse. The carbon fiber, which required enormous energy to produce from polyacrylonitrile precursor fiber through an oxidation and carbonization process running at 400 degrees Celsius, is destroyed. In an era of tightening EU end-of-life vehicle regulations, escalating corporate sustainability commitments, and genuine institutional pressure on manufacturers to demonstrate circular economy compliance, this is not just an inconvenience. It is an existential barrier to thermoset carbon fiber adoption at automotive mass production scale. You cannot build 2 million vehicles per year using a material that sends 15 kilograms of unrecyclable composite to landfill per vehicle at end of life, and simultaneously claim compliance with 2030 EU sustainability directives. The math does not work. The regulators will not accept it. The institutional investors tracking ESG metrics will not accept it. CFRTP is thermoplastic. The chemistry is fundamentally different, and the recycling implications are transformational. Heat the material past the thermoplastic matrix melting point, typically 200 to 260 degrees Celsius, depending on the specific polymer used, and the carbon fibers separate cleanly from the resin, without chemical degradation. Both components are fully recoverable. The recovered carbon fiber retains its tensile properties and can be reprocessed into new CFRTP material for second-generation automotive or industrial applications. The thermoplastic resin enters standard polymer recycling streams. Nothing goes to landfill. Toray Industries has demonstrated this closed-loop recycling process at their Shizuoka manufacturing facility at industrial scale. Their published process data shows 95% carbon fiber recovery from end-of-life CFRTP components, with no measurable degradation in tensile strength, meaning the recovered fiber from a scrapped 2030 Toyota is a viable raw material input for a 2035 Toyota. The circular economy application is not theoretical. It is operating now. The EU's end-of-life vehicle directive, currently being revised for 2030 and 2035 implementation cycles, is widely expected to mandate minimum recycled content percentages in new vehicle structural materials and maximum landfill percentages for end-of-life vehicles. CFRTP meets both requirements cleanly. Aluminum meets them marginally. Aluminum recycling is well established but energy-intensive. Thermoset carbon fiber fails the landfill requirement completely and has no viable path to compliance. Regulation is about to force the entire global automotive industry in exactly the direction Japan already went a decade ago. The manufacturers who are building CFRTP production infrastructure now will be in compliance by default in 2030. The manufacturers still betting on aluminum and thermoset carbon fiber will be facing retrofit costs, supply chain restructuring, and regulatory penalties simultaneously. Toyota, Toray, Honda, and Subaru are not ahead of the regulation by accident. They helped write the technical standards that the regulation is based on. And here is rule number 5, the one that directly and immediately affects what you pay for your next car, and the timeline every buyer needs to understand right now. Mass production. CFRTP structural components currently cost approximately 2.8 times the equivalent aluminum component in per unit production cost. That is the number that has kept this technology out of mainstream vehicles so far, and the number that every skeptic cites when dismissing CFRTP as a premium-only material. And it is a real number. At 2.8x aluminum cost, CFRTP in a $28,000 vehicle adds $3,200 to $4,800 to the bill of materials depending on how extensively it is used in the structure. That premium either comes out of margin or goes onto the sticker price. Neither option works at volume in a competitive mass market, but that cost premium exists for a specific and temporary reason. There are currently 2 primary manufacturing facilities in the world operating CFRTP production at automotive scale. Toray's primary Japanese facilities in Ehime and Aichi prefectures, and their joint venture plant in Spartanburg, South Carolina, which supplies the BMW manufacturing cluster in that region. 2 facilities. Global automotive demand. Constrained supply against growing demand is the entire explanation for the 2.8x cost premium. It is not a materials cost problem. It is a production infrastructure problem. That infrastructure is being built right now. Toray has publicly committed to a capital expenditure program exceeding $2 billion through 2030, specifically targeting automotive-scale CFRTP production capacity expansion across Japan, the United States, and France. Their publicly stated cost target is parity with aluminum structural components by 2030, achieved through scaled production volume, reducing per unit fixed cost allocation, second-generation automated fiber placement technology, reducing cycle times from 60 seconds to under 20 seconds per component, and thermoplastic resin formulation improvements, reducing raw material cost per kilogram. Every comparable advanced material introduction in automotive history follows the same cost curve. High-strength steel was a premium material in 1995 and is now in every $18,000 economy car. Aluminum was exotic in the 1994 Audi A8 and is now standard in $32,000 pickup trucks. The cost curve on advanced materials in automotive production moves in one direction once the production infrastructure investment decision has been made. Toray has made that decision. The $1.2 billion is committed. The curve is moving. When CFRTP crosses cost parity with aluminum, and the production investment trajectory says that happens between 2029 and 2032, the technology does not gradually filter into parity in mainstream vehicles. It cascades. Every platform being engineered today for 2030 production launch is making material decisions right now. The platforms that choose CFRTP for their 2030 launch will have structural cost parity with aluminum by the time they reach peak production volume in 2032 to 2033. The platforms that choose aluminum for their 2030 launch will be re-engineering for CFRTP in their 2035 refresh, a cycle behind, paying the re-engineering costs that the early adopters already paid. What this means practically for every car buyer reading this today: any vehicle you purchase in the premium segment above $50, 0 inches the next 2 to 3 years will begin showing CFRTP and structural floor, firewall, and pillar elements. Look for it in the specifications under carbon fiber reinforced thermoplastic structural elements or advanced composite body structure. Any vehicle you purchase after 2030 at any price point above $30,000 will likely have CFRTP throughout the primary body structure as standard architecture. And the vehicles being engineered right now, the 2028 and 2029 model year platforms currently in clay model and structural simulation phase, are being designed around this. Material from the first engineering review. Japan spent 20 years solving a problem that the rest of the automotive world said could not be solved at production scale. A Toyota engineer got laughed out of a Detroit conference in 2019 for presenting the production stamping data. The same data is now in BMW's supplier specification documents. The laughing stopped. The cease and desist letters started. The $1.2 billion capital commitment is public record. That is usually how you know something is not just real, it is already over. The transition already happened. Most people just don't know it yet. Hit subscribe because next week we are going platform by platform through every major vehicle, launching between 2026 and 2030, identifying exactly which ones are built on CFRTP architecture and which ones are still betting on aluminum. And that information will tell you which cars hold their value through the next decade, and which ones become the next generation of rapidly depreciating legacy technology.